let's go ahead and continue. Thank you. Talking about interval of convergence slash radius of convergence. This pen, not my phone. So, interval of convergence. This pen also is in that place. The pens are dying. Welcome. Cool. Looks good. Thank you. All right. And so kind of the first thing I want to make you aware of or remind you of is the following. And that's the integration slash differentiation theorem. Which basically just says the following. If you integrate or differentiate a power series that converges for some radius of convergence, the derivative or the integral will also converge for the same radius of convergence. So let's write it out. If we integrate or differentiate a series that converges for x between negative r and positive r, or really actually x between a plus r and a minus r. The new series also converges on the same radius. The difference between the two ways I'm writing it here is this way of writing where x is between negative r and r is if your series is centered at 0. And this other way of writing it where x is between a minus r and a plus r is if your series is centered at a, which we haven't really talked about differing where we center them, but we will. The only difference is that for this derivative or antiderivative of your series, here we're going to have to test the endpoints. Welcome. So let's look at an example. A lot of this also is going to use the tricks of writing a series. So let's find, we're going to use this series to find a series and where it converges, because really we can't or shouldn't talk about a pair series if we're not also talking about where it converges. It doesn't make sense to say a function equals some series if you don't actually mention where they are equal to each other, right? Just as a point, it doesn't really make a lot of sense to say 1/1 minus x equals the sum from n equals 0 to infinity of x to the n without talking about where that's true, right? That's not always true. That's only true if x is between -1 and 1. Sorry, my x there was kind of stupid because I was trying to write a 1 instead of an x, right? So we can only say this is true on the interval of convergence. So in other words, the interval of convergence is -1 to 1, and the radius of convergence is 1. And again, I would encourage you to think of the radius of convergence as half the length of the diameter of convergence, where the diameter of convergence is literally just how long the interval is. I know no one ever says the words diameter of convergence, but that's right. If you go from end to end of a circle, you get the diameter. So if you cut that in half, you get the radius. So this is kind of like the end to end of the circle. And its length is 2, so the radius is 1. So let's go back to this problem here. I want to use the 1/1 plus x squared to find a series. I stopped saying all the words. Sorry. There's one more word there. Find a series for the inverse tangent of x. Sorry, I got distracted by my own thoughts. And you might think those don't look a lot alike. You might also think one of those things looks like the derivative of the other. And that's what we're going to do. So we're going to start with the one that we might be more likely to write a series for. I think we might have a good idea of how to write a series for 1/1 plus x squared. I'm not going to do it. Well, I'm not going to do it using Taylor's formula, which you may or may not have talked about yet. I don't want to do this the hard way. I want to do it the easy way, meaning I'm always trying to make my series, I should say my function, to make it look like a series. I want to make it look like 1/1 minus something. That is always what I'm trying to do, because I know that 1/1 minus something, or really the top doesn't have to be 1. You can have anything else on top. Something over 1 minus something is key. Something over 1 minus something is the sum from n equals 0 to infinity of that ratio to the nth power. Or if you want to write out the long way, that's going to be 1 minus x squared plus x to the 4th minus x to the 6th, and so on and so on and so on. Great. And now what we're going to do to both sides of this thing is we're going to anti-differentiate both sides, so that the antiderivative of 1/1 plus x squared is equal to the antiderivative of, I find it easier to write it out, although really you can do it either way. Although I do think it's easier if you write it out. It helps. It's going to be easier to see what the formula should be if we write it out the long way. Although, well, we'll go back and see. Antiderivative of 1/1 plus x squared is the inverse tangent, or if you prefer, the arc tangent of x. Either way is correct. And that's going to equal, let's see, so if I anti-differentiate this term by term, I'm going to get x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7, and so on and so on. And looking at that, I think we can see a pattern for it. That's looking like the sum. Now be careful, I am going to change where my index is starting here. I'm going to go the sum from n equals, I guess it doesn't really matter. You could go 0 or 1. I guess I'll go 0 to be more consistent. From n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1. That's mostly right. What am I missing? I got x to the right power. I'm dividing by the right thing, but I've forgotten the the alternating part. Where did you get arctangent? Oh, good question. So the arctangent came from the question, but we're getting it from the fact that we know, or we were supposed to have learned in 21A, this is 21B, in one of those classes, 21A or 21B, that the derivative of the arctangent of x is equal to 1/1 plus x squared. That's where that's coming from. In a similar way, although it's less, you wouldn't really ask the question, but you would also could have seen at some point that the derivative of the arc sine of x, or the inverse sine of x, is 1 over the square root of 1 minus x squared. So that's where that's coming from. But yeah, I forgot the -1 to the, I always start with n and then I check. If I plug in n equals 0, do I get the right sign when I start? If I plug in 0, I get -1 to the 0, which is 1. I'm starting with a positive. Great, I'm on the right sign. But if I had the wrong sign, I would just add a 1 up there to make it the right sign. So it started with a negative instead of a positive. Oh yeah, here's what I wanted to point out. You totally could do this more formulaically, meaning if you wanted to, you could actually integrate the sum. Fun fact, integrals pass through sums as long as the things work the way they're supposed to. And I'm going to rewrite this as the integral of the sum from n equals 0 to infinity. I'm going to rewrite this as -1 to the n times x to the 2n. And now I'm going to rewrite this as the sum from n equals 0 to infinity of -1 to the n times the integral of x to the 2n. And oh, look, the integral of x to the 2n is exactly x to the 2n plus 1 over 2n plus 1. Totally works. So you can think of it term by term and see the pattern that way, or you really legitly can just simplify this so you have the x's kind of separate from everything else and then integrate the x part. Right? So I broke it up as -1 to the n times x to the 2n, and then I anti-differentiated with respect to x. And the antiderivative of x to the 2n is x to the 2n plus 1 over 2n plus 1. You don't have to do it that way. So we've got the power series for the inverse tangent, but we need to know where it converges, right? Because again, it's not always true that arctangent of x is equal to this, right? Arctangent of 2, I'm going to tell you, isn't equal to 2 minus 8/3 plus 32/5 plus et cetera, et cetera, et cetera. It only works for values where it converges. So our interval of convergence here, we know that since, well, let's look back at the original thing before we anti-differentiated. 1 over 1 minus negative x squared converges if the ratio, which is negative x squared in absolute value, is less than 1. And that's always the nice thing about writing it, looking at something like this. Something like this, you can just say, hey, my ratio has to be between -1 and 1. There's no other choice. That's geometric. Geometric series only converges if the ratio is between -1 and 1. So we can kind of figure out that that means, oh, that's going to mean that x has to be between -1 and 1. Right? X can't be 1, x can't be -1, x can't be any bigger than that or any more negative than -1. And then we can say that this new series, arctangent of x equal to the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1, also converges if x is less than 1, bigger than -1. But this is not geometric. So unlike a geometric series, we have to check the endpoints. So we're going to have to check when x is equal to 1 and when x is equal to -1. So we check the endpoints. Let's see what we get. So if we let x equal to 1. Now, when you're checking the endpoints, what you're actually doing is you're just substituting x equal to 1 back into the series you have. So we have that the series from n equals 0 to infinity of x to the 2n plus 1 over 2n plus 1 times -1 to the n. I'm just going to plug in 1 for x. And we're going to get the series from n equals 0 to infinity of 1 to the 2n plus 1 over 2n plus 1 times -1 to the n. 1 to any power is 1. So we're going to write this as the series from n equals 0 to infinity of -1 to the n over 2n plus 1. All right. This series is alternating. And it definitely meets all the criteria of the alternating series test. It's definitely, the non-alternating part definitely has a limit that's 0, and the non-alternating part is definitely decreasing. Typically, when you're testing an endpoint, you don't go through the work of showing all the things for an alternating series. You just say, hey, I know that this converges, and it would converge by the alternating series test. It wouldn't converge by any other test, though. This would not converge absolutely. If you took the absolute value of this, it would definitely be divergent because it looks like a P series where the power is 1. How did I set absolute value of x squared less than 1 again? So all I was doing there was saying, sorry, I don't cover up that right there, right? That since we're talking about this 1 over 1 minus our ratio being convergent, Well, we know that a geometric series is convergent. This is a geometric, or the series for this, which is, sorry. Right? We know that a geometric series is convergent if and only if the ratio is between -1 and 1. So what we're saying here is, oh yeah, we need this ratio, which is -x², to be less than 1 in absolute value. Or if you want, you can write that as -x² less than 1, bigger than -1. I didn't show all the work because I was being a little lazy. But if you want to show all the work, we can multiply everything by -1 and get 1 bigger than x², bigger than -1. And then for x² to be between -1 and 1, we have to have that x itself is between -1 and 1. There's no other way for a power of x to be between 1 and -1 unless x is between -1 and 1. All right, so we checked one endpoint, it converged there. Let's check the other endpoints. So this is where we have to be extra careful. If we check x equal to -1, we're going to get the sum from n equals 0 to infinity of -1 to the 2n plus 1 times -1 to the n over 2n plus 1. So let me ask you all, is this alternating or not? Good question. You could combine it together and write it as -1 to the 3n plus 1, and then think about what your powers are doing. Or you could justify to yourself that -1 to the 2n plus 1, well, 2n plus 1 is always an odd number. So this part here is always equal to just -1, which means we really just have, if you want to rewrite it, the sum from n equals 0 to infinity of -1 to the n plus 1 over 2n plus 1, which is alternating, right? You have this thing that's always -1 times something that's changing signs every time. So also converges by the alternating series test. So just be careful with your powers. Basically, something's going to be alternating if the power on -1 is something that's changing parity, right? Is going from a power of odd to a power of even, power of odd, power of even, right? You could, if you had written this as -1 to the 3n plus 1, you can see the 3n plus 1 changes from odd to even every time you increase n, right? If n is 1 or if n is 0, you get 1. If n is 1, you get 4, then 7, right? That's going to give you a positive, a negative, a positive, a negative, a positive, a negative. So our interval of convergence here, we're including both of the endpoints, both x equal to 1 and x equal to -1. So our interval of convergence is actually -1 to 1 inclusive of both endpoints. Our radius of convergence hasn't changed. So the radius of convergence when you differentiate or anti-differentiate literally never changes. It's always the same. Radius of convergence is still r equal to 1. And then I've seen this question floating around some people's homework assignments, so I might as well say it here. If you want to talk about where, oh gosh, what's the word I'm looking for? Where is this thing? So specifically, this series arc tangent of x equal to the sum from n equals 0 to infinity from -1 to the n times x to the 2n plus 1 over 2n plus 1. This series is conditionally convergent where? Good question. So when you're finding where a series is convergent, it's always absolutely convergent on the inner part, like the not including the endpoints part. And then if it's convergent at the endpoint, it is typically, although not all, I shouldn't say that actually. I take back what I was about to say there. We don't actually know. I will tell you this one is conditionally convergent at the endpoints because it's certainly, if you plug in 1, right, that series there is a conditionally convergent series. It does not converge if you take the absolute value of the terms. Similarly here, this is also for the same reason conditionally convergent. It is not absolutely convergent here. So we would say that this series is conditionally convergent on this set, which is kind of an annoying way to have to write your answer, but it is the way that WebWork wants your answer. So this is how you would say where it's conditionally convergent. Conditionally convergent there, interval of convergence there, and I guess I suppose I should also point out it is absolutely convergent on questions so far. Yeah.
Usually, I'm doing a couple things, but I'll like start with the where did the -1 and 1 come from? Is that like,
Oh, sure.
isn't it different for every problem?
Yes. So here we knew because the original series converged on the interval from -1 to 1 that the derivative or the antiderivative also has to converge on the same interval. The difference is we might have to check the endpoints. Let's actually explore that a little bit further because it's a question that's worth exploring. So let me just point out. Here is our original series. Sum of one, not the sum, sorry, apologies. Let's just kill that piece of paper. Die. Okay. So our original series was this. Right. Now, really, you could find where this converges by using the ratio test. So ratio test, we take the limit as n goes to infinity of the n+1 term over the n term in absolute value. Right, ratio test. And then that ratio has to be less than what? Right, 1. So if we simplify this, well, it simplifies really, right? Ratio test is always super straightforward for a geometric series. The things just cancel and you get the ratio. So this is equal to the limit as n goes to infinity of the absolute value of -x². And then the limit of that, there is no more n. So I just say, well, the limit's just that, the constant -x². Yes, -x² is a constant in this context. And then that's less than 1. And then we end up getting, oh yeah, x is between -1 and 1. And then instead of using the ratio test for the new series, the antiderivative, we just said, well, they have to converge on the same interval, except we have to test the endpoints, but we can check. So let's check real quick. Actually, I should point out one more thing. This series definitely does not converge when x is equal to 1 or x is equal to -1. Right? That's always true for a geometric series. It doesn't converge when the ratio is 1 or -1. Because what would we get if x was 1? We would get the sum of -1 to the n, which is divergent. Right? You're getting 1, -1, +1, -1, +1. Right? That doesn't ever get close to 1 value. It goes back and forth between 1 and 0. Right? Not 1, 1, -1, 1 and 0 is 1, then -1 is 0, then +1 is 1. Right? Okay. And same deal if you plugged in x equal to -1, you get actually the same exact thing. So when we look at the inverse tangent series, which is the sum from n equals 0 to infinity of -1 to the n times x to the 2n plus 1 over 2n plus 1. What we're doing when we use the theorem is we're saying we know that if we did the work we're about to do, we're going to get the same interval, except maybe the endpoints we have to check. But here's the work we would have done if we weren't using the theorem. We're going to use the ratio test again. So using the ratio test, thank you. We're going to do the limit as n goes to infinity of the absolute value of the n+1 term, which is going to be a little bit wonkier here, to be -1 to the n+1 times x to the 2 times n plus 1 is 2n plus 2, plus another one is 2n plus 3 over 2n plus 3 times 2n plus 1 over -1 to the n times x to the 2n plus 1. Looks a little gross. It's not that bad. So the -1 to the n plus 1 over the -1 to the n becomes just a -1. The x to the 2n plus 3 divided by x to the 2n plus 1 just becomes an x squared. And the 2n plus 1 over 2n plus 3, well, that's going to stick around, but all of you should be able to tell me that the limit as n goes to infinity of 2n plus 1 over 2n plus 3 is what? Yeah, thank you. Yes, exactly that many. It's 1. So I'm going to get the absolute value of negative x squared. Well, look, I'm getting the same ratio as before. Now, the only difference is this thing isn't actually geometric. So it's acting like a geometric series whose ratio is negative x squared. But we know that for an actual geometric series, it doesn't converge when the ratio is 1 or negative 1. But for this thing that's not actually a geometric series, we certainly need the ratio test to have a value that's less than 1, which is going to result in x being between negative 1 and 1. But now if it's equal to 1, the test is inconclusive, meaning we actually need to go and check those points. So that's why we check what values of x give us an inconclusive result from the ratio test. In this case, x equal to 1 and x equal to negative 1, or more generally, just whatever your endpoints are. Let's look at another example, which might be a little more illuminating than this example. Not that this example isn't good, just there's lots of examples. Yeah. Completely, yeah, totally ignore that negative 1. I would normally, once I like from here, I would just be like, bam, bam, yeah, they're done. Yes, I know there's a negative 1 left over, but the absolute value of negative 1 is just 1. And it's also totally fine to say the absolute value of negative x squared is equal to the absolute value of x squared. That is also true because the absolute value of a product is equal to the product of the absolute values. So it's totally fine to just do away with any negatives you have that are multiples in there. All right, have another example. Yeah, let's look at that one. Cool. So let's look at this series here. The series from n equals 1 to infinity of x minus 3 to the nth power over n to the 4th times 2 to the n plus 3. Oops, sorry. And we want to find all the things, meaning find the interval of convergence. Really, the interval of convergence is like usually the thing that's kind of the, if I was going to ask a question, that's the one I would ask. So I feel like that's the one we have to work the hardest. That's where you have to do the most things. You have to find out the radius of convergence, or you should be able to find it very easily from the interval of convergence. And then you can also talk about absolute versus not. So to find the interval of convergence, ratio test, ratio test every time. That's the, I mean, if you had something that happened to be everything raised to the nth power, you should just say it's geometric and be like, there's my ratio. But you could also use the nth root test if you were a glutton for punishment. But you should almost never be using the nth root test in this context. Whenever you have something like this, where it's a power series and you're trying to find the interval or radius of convergence, ratio test is the way to go every time. No ifs, ands, or buts about it, with maybe small exceptions. Okay, so we're doing the limit as n goes to infinity. You really do need the absolute values here, right? Because you have x and we're actually trying to find the values for x. So the absolute value is necessary. We have x minus 3 to the n plus 1 over n plus 1 to the 4th times 2 to the n plus 1 plus 3, which is n plus 4, times the reciprocal, n to the 4th, 2 to the n plus 3 over x minus 3 to the n. Now, in my opinion, you all probably could write the answer to this in one step. X to the 3 to the n, x minus 3 to the n plus 1 over x minus 3 to the n is just x minus 3. 2 to the n plus 3 divided by 2 to the n plus 4, what's that leave me with? A 2 somewhere in the denominator. And then the limit of n to the 4th over n plus 1 to the 4th is 1. So I feel like you all could go straight from here to here without too much trouble. Now, if you want to show an additional step, you could show the following. We have x minus 3 to the n plus 1 over x minus 3 to the n We have 2 to the n plus 3 over 2 to the n plus 4. And we have n to the 4th over n plus 1 to the 4th. This becomes your x minus 3. This becomes your 1/2. This has a limit is 1. So I really should point out that's not equal to 1, but it goes to 1 as n goes to infinity. And then, all right, and then I think, I mean, there's so many ways you could do this. I personally like to, once I get to this stage, some people like to multiply by 2 first. That's fine. You can do that if you want. I like to drop the absolute values and say, okay, x minus 3 over 2 is between 1 and -1. That's where I would go first. And then multiply everything by 2. -2 is less than x minus 3 is less than 2. And then add 3 to everything. 1 is less than x is less than 5. We're not done. So our interval of convergence right now could be one of 4 things. It could either be 1 to 5, or it could be 1 to 5, or it could be, whoops, not that, or it could be 1 to 5, or it could be 1 to 5. One of those is our interval of convergence. We know it converges, we know it converges absolutely on this. So for sure, it converges absolutely there. Because I know I've said this before, I'm going to say it again. When you do the ratio test and you get convergence, you get absolute convergence. So whenever you're doing the ratio test and you find that something converges, you have shown it absolutely converges on whatever your interval is. Question? Okay, cool. Now, that doesn't mean it couldn't absolutely converge to one of the endpoints. We're going to check the endpoints and see. So let's check. Do I have enough room? Yeah, I have enough room. Let's check x equal to 1. 1 first? Yeah, 1 first. Why not? So if I plug in x equal to 1, I'm going to get the sum. You want to see the things maybe. We plug in x equal to 1, we're going to get 1 minus 3 to the n over n to the 4th times 2 to the n plus 3. So when I plug in x equal to 1, I'm going to get the sum. I'm not going to write the n equals whatever. You know it's there. We're going to get 1 minus 3 to the n over n to the 4th times 2 to the n plus 3. Okay, it's a little hard to see what's happening if you write it like that. There's a really, really easy thing you can almost always do to deal with a negative number to the n. Rewrite this as the sum of -1 to the n times 2 to the n over n to the 4th times 2 to the n plus 3. I would always recommend doing that because then 2 to the n over 2 to the n plus 3, I can rewrite this as the sum of -1 to the n over 2 to the n divided by 2 to the n plus 3 just gives me a 2 to the 3rd on the bottom, which is 8. All right. So this series, is it convergent? That's not a good question. I already asked it the wrong way. Is it divergent? No. Is it absolutely convergent or is it conditionally convergent? Well, oh, yeah? I heard someone like unmute themselves for a second. You're welcome to chime in.
Yeah, conditionally.
What was that?
Conditionally.
Oh, I think it's actually absolutely. But let's check and see. So if we took the absolute value of this, we get the sum of 1 over 8n to the 4th. Does that converge?
That converges, yes.
Definitely. Right, this is a convergent p-series. So that means that we actually have absolute convergence at x equal to 1. Again, this is not a question I'm used to asking. Like usually nobody really cares, except for web work apparently, if your series converges absolutely or converges conditionally at the endpoint. Usually when we're asking for the interval of convergence, we're just like, where does it converge? I don't actually care what kind of convergence you have. But since you guys are getting asked these questions, I feel like it's worth it. Let's look at x equal to -1. No, -1. Let's not look at x equal to -1. What should I actually be looking at?
X equals 5.
Thank you. Yes. Right. The other endpoint. I was thinking of the other problem where it was -1. So we plug in 5. We're going to get the sum. Let's see if I can keep this. Yeah. Of 5 minus 3. So 2 to the n over n to the 4th times 2 to the n plus 3, which is actually going to be the sum of 1 over, again, 8 times n to the 4th. Is that convergent?
Yes.
I mean, yeah, right? Because it was over here. And also, if you see something that's convergent and it's not alternating, then it's automatically absolutely convergent, right? Because you took the absolute value of it, it wouldn't change. So this is also absolutely convergent. So we could say that for this series, the interval of convergence is bracket 1 to bracket 5. And I suppose we would also say that's the interval of absolute convergence. It also absolutely converges on the same interval. It doesn't conditionally converge anywhere. What does it do everywhere else? Like if I said, what about x equal to 6?
Diverges.
Right, this would diverge if x equal to 6. Explain, yeah. So the brackets versus the parentheses, the brackets mean we want to include the 1. So when I write a bracket like that, I'm saying I'm including 1. So I'm including the fact that it converges at 1. This is the interval of convergence. So this is not the answer because it excludes both 1 and 5. This is not the answer because it excludes 1 and includes 5. And this is not the answer because it includes 1 but excludes 5. This is our answer. It includes both of the endpoints, which in this problem happen to show convergence.
So like when we have like x equals 1, x equals 5, it's like numbers for x since we know x in this equation.
Oh, there's an x. It's right there.
Oh.
So we are literally plugging the x value back into the power series where x is. And it's something that you're definitely not the only one that might miss that. I've definitely seen lots of students be like, what are we doing with this endpoint? We are actually just saying, I'm going to plug in this value right there. That's how I got 1 minus 3, which is -2 to the nth.
Yeah.
And when I plugged in x equal to 5, that's how I got 5 minus 3, which is 2 to the nth. I'm really actually just substituting. The way I got the 8 in the denominator was 2 to the n over 2 to the n plus 3. You can think of that as, I would just write it as 2 to the n minus n plus 3, which is then 2 to the -3rd, which is 1 over 2 to the 3rd, which is 1 over 8. That's how we're getting that. Okay. Hi, everyone. Oh, question.
So how do we find the power series?
Wait, say that one more time.
So how do we find the power series that converge
So this one there isn't. So this one doesn't converge conditionally anywhere. The previous one. So here's what I should say. The power series will always converge absolutely on the interval that excludes the endpoints. So if you're doing, I'll come back to this in just a second, but here's what I'll say. So if you have some power series, sum from n equals, let's say 1 to infinity, of some power series, it's always going to absolutely converge on whatever your exclusive interval convergence is, whatever those numbers are. So in this case, well, I should really just say on a minus r to a plus r. Always, every time, because when you're doing the ratio test, you're always getting the interval of convergence where it's, like in the previous example, we're doing the ratio test and we're getting the absolute value of x minus 3 over 2 less than 1. And when the ratio test is less than 1, that gives you absolute convergence. And then you solve this and you get x between 1 and 5. And then the endpoints are a total crapshoot. Anything can happen in the endpoints. You can get straight divergence, you can get conditional convergence, or you can get absolute convergence. Anything can happen. So we have to check. But to more generally answer your question, what that typically means is if you're being asked, you can usually, I've only ever seen this, literally this is the first quarter I've ever seen anything ask this question, where they're like, what's the interval where it conditionally converges, where does it absolutely, right? The only place it can really conditionally converge are possibly at the endpoints. You can't get conditional convergence anywhere else because anywhere inside the interval, you get absolute convergence.
That's all that question on my question.
Really?
Yeah.
Wow. Well, that's a new one to me. No, definitely not. Although both of our examples have shown that. Let me give you another, let's look at another example where that doesn't happen.
I know there's like work to show how to get one radius.
Yes. Oh, radius. That's what I was about to go. So it's good. Back to this one. So looking at this interval of convergence, everyone should show me on their fingers or type in the chat what the radius, not the diameter, what the radius of convergence is. I would love to see that number on your fingers. Yes. Yes. I'm seeing one too many fingers on a couple people there. Okay, well, I'm seeing 2s and 3s. So the interval, so 3 is an answer to a different question. So the radius of convergence is definitely half the diameter, which is, well, the diameter or the length of the interval is 4. So the radius is going to be 2. The 3 that I saw some people answering and some people writing in the chat is that's what the center of this interval is. So this power series has a center of 3. And the center, I always think of it as just if the number that if you plugged it in, every term would be 0. If you plugged in 3 for x, you're going to get 0 plus 0 plus 0 plus 0. Not very exciting. But a power series always converges at its center. If you plug in 3, well, of course it's going to converge. You're going to add up a million zeros. That's still 0. And then the radius here is 2. There are ways to find it. You can look at kind of this and see that if you have x divided by a number, that number is your radius. I feel like it's too much of a formula to remember, though. I would really strongly encourage you to just say, if you know the interval is, oh, no, that's, yeah. That's not a negative one. That's a positive one right there. Yeah, if it was a negative one, then your radius would be 3. But yeah, I would encourage you just to find the length of your interval and divide it by 2 if you're asked to find the radius. Okay, all right, let's do another example. Yeah, we got time, we got plenty of time. Let's not do that example. Let's do this example. So let's see how to make it fun and exciting and interesting. Sure, let's look at the sum from n equals 2 to infinity. Yeah, do that. Okay, sure. Sorry, I have to think for a minute here. Let's say it's x to the, yeah, we don't want to be too fancy, otherwise it's not going to work, over 3 to the n times the square root of n. Oh, I want to make that a little more exciting. Let's make it, I'm going to fix it, sorry. I want to make it a little more interesting, apologies. Let's do an x plus 2 to the n over 3 to the n times the square root of n. Okay. So we're being asked to find the interval of convergence and everything else implied by that. Interval of convergence, radius of convergence, interval of absolute convergence, and then where it conditionally converges. Sorry, too many words to write. I can't write them all. You just have to know that that's what they all mean. This is absolute. Okay, so we're going to find all the things that WebWork could ever ask you to find. And we're going to start, of course, with what thing am I going to do first?
Ratio test.
Yeah, exactly, the ratio test. Cool. So a couple things to be aware of when you do the ratio test. Powers of n are almost completely inconsequential, right? When you did the ratio test of the previous problem, that n to the fourth didn't do anything, right? N to the fourth over n plus 1 to the fourth, that limit became 1. And that is almost, I can't think of a time where that wouldn't be the case. So the only time you have really kind of funky stuff happening is when you might have like an n factorial or something like that, but really like n to a power, n squared, n cubed, square root of n really doesn't contribute anything. We still need to write it down when we do it, but you should just be aware that that part's just going to give us the 1. Okay, so let's see here. Something else over here, 1 second. So we're going to do the limit. N goes to infinity. See, I have an x plus 2 to the n plus 1 over 3 to the n plus 1 times the square root of n plus 1 times reciprocal time 3 to the n times the square root of n over x plus 2 to the n. Okay, and then grouping like things together. You can do, I would encourage you to simplify in this step. I'm not going to, but you can and should. X plus 2 to the n plus 1 over x plus 2 to the n. That's just an x plus 2. 3 to the n over 3 to the n plus 1. That's just a 1/3. And the square root of n over the square root of n plus 1. If it makes you feel better, or if you want, you might write this as the square root of n over n plus 1 to see that its limit is going to be the square root of 1, which is 1, but not necessary or required. So this is going to end up equaling the absolute value of x plus 2 times 1/3 times 1. And that's going to be less than 1 for convergence. And at this stage, you might be able to make the observation that the radius of convergence is how many? The answer some people wanted it to be last time. Yeah, this time it is 3. So if you have 1x, really, I should just say the radius of convergence is the reciprocal of the coefficient of x. So if x is multiplied by 1/3, your radius of convergence is 3. If x is multiplied by 5/2, your radius of convergence is 2/5. So that's one way you can find it without doing all the other work. I like doing it. Usually you have to do all the other work though, so it kind of doesn't really make sense to memorize that particular fact. Let's see. So I'm going to have x plus 2 times 1/3 less than 1 bigger than -1. I'm going to have -3 less than x plus 2 less than 3. And then I'm going to get subtracting 2 from both sides, -5 less than x less than 1. And I know for sure that the series converges absolutely on that interval. It might also converge absolutely at the endpoints, but it might not. It might not even converge at all at the endpoints. We have to check them. So let's check the endpoints. So once again, we are looking at this series from n equals 2 to infinity of x plus 2 to the n over 3 to the n times the square root of n. Something I have learned over the years is that if you have one endpoint that's going to make it alternate and one endpoint that isn't, check the one that isn't first. And here's why. If you check the one that makes it not alternate first and it converges, then you know that the alternating one's automatically going to converge because it's going to absolutely converge. This is not going to give you that, but like in the previous problem we were doing, sorry, let me go back right now. So in this problem we were doing here, it actually would have been to my benefit to check the x equals 5 one first. So if I'd done that one first, I would have seen that this converges, absolutely. And then when I did the x equals 1, I would have had the same thing except it's alternating. But if the non-alternating series converges, then the alternating series also converges absolutely, as this converges absolutely. So if you can see that plugging in one value is going to make it not alternate, and the other value is going to make it alternate, do the not alternating one first. So I can see that if I plug in x equals 1, I'm going to get 3 to the n over 3 to the n, which is going to not alternate. So let's do that one first. So if I plug in x equal to 1, I'm going to get the sum. And let's actually just write it out. So we're actually plugging it in. I'm plugging in x equal to 1. So I'm getting 1 plus 2 to the n over 3 to the n times the square root of n. But then 3 to the n over 3 to the n cancels out. So you get the sum from n equals 2 to infinity of 1 over the square root of n. And that series is
Divergent.
Divergent. Like that really wonderful movie. Kidding. It's mediocre at best.
Never watched it.
Yeah, you're not missing out. So that doesn't really help us with the other one, but it does. Well, actually, here's what it does still help us with the other one. Actually, we know that we can't show the other one converges by absolute convergence, because if we take the absolute value of it, it's not going to converge. So the other one we kind of already know if it's alternating, we're going to have to do the alternating series test. So now let's plug in x equal to -5. We're going to get the sum from n equals 2 to infinity of -5 plus 2 to the n over 3 to the n times the square root of n. And that's going to become -3 to the n over 3 to the n times the square root of n. And you should get used to seeing if you have negative number to the n over positive number to the n, that's just going to reduce to -1 to the n. You can either do -3 over 3 to the n, you can write -3 to the n as -1 to the n times 3 to the n, but it all boils down to, I'm going to have a -1 to the n over the square root of n. And I think at this point, you should say, you shouldn't show all the 3 steps. You should be like, boom, that converges by the alternating series test. You can check the things if you feel like you have to, or if your teacher tells you you have to. And the things you would have to check are 1, the non-alternating terms are positive. Yeah, they're positive. 2, the limit of the non-alternating terms is 0, definitely. And 3, the non-alternating terms are decreasing, meaning the next term is smaller than the previous term. Yeah, I think you're pretty safe to say that that's true.
We always do the absolute convergence set.
The alternating series. That's what AST is, the alternating series
We
test.
always do the alternating series test whenever we do the IOC.
Not always, but if we have to. So like the previous one, back to this example again. Here, when I plugged in 1, got -2 to the n, I didn't actually use the alternating series test because I saw that if I took the absolute value of it, I would get something that was convergent. So I could just say absolutely converged. But if it hadn't worked, no, excuse me, if that hadn't worked, then I would have gone to the alternating series test. Yeah. So here, I already knew that the absolute convergence test wasn't going to work because that thing diverged. If I took the absolute value of that, it's going to be that. So I jumped straight to the alternating series test because that's kind of the only choices you have for an alternating series. Either you check to see if it's absolutely convergent, and if it is, great, you're done. If it isn't, you have to go to alternating series test. But really, those are the only choices you have. Yeah. Yeah. Right. You're 100% correct. But I know you're asking me a question, right? So this is divergent as a P series. P series diverges if P is less than or equal to 1, converges if P is greater than 1. No. Here's why. P series specifically has to be a series of positive terms. So P series, here's the only way you can really mess with the P series. So I actually didn't even write this as well as I should. So technically what we really should say is for a P series, it's the sum from n equals 1 to infinity of 1 over n to some power. And you're technically supposed to start at 1. But really, I should actually say, so this converges if whatever, diverges if whatever. But really, you can extend this to, you can actually take any non-zero multiple of it. So you can say multiply by like k, over n to the p. And you can actually start anywhere after 1. So really, you can start at n equals any value, let's say j, where j is greater than or equal to 1. Because really, starting later just means you're cutting off some finite number of terms. And so if the whole thing converged and you cut off some finite number, it still converges. If the whole thing diverged, cut off some finite number, it still diverges, right? Just cutting off a finite amount of something never changes its convergence or divergence. And then also multiplying the whole thing by a constant. Well, if it converges and you multiply it by 5, it still converges. If it diverges, multiply by 5, it still diverges.
So we got right there in the column is conditionally convergent.
Right, exactly. We're about to say that. So this is definitely conditionally convergent at x equal to -5. So here are all the things that I would say about this series. The interval of convergence, which is the thing I care the most about, because that's what I always to me, that's the most interesting thing. The interval of convergence is going to be from exclusive of 1, sorry, 1's the right endpoint, blah, inclusive of -5 to exclusive of 1. The interval of absolute convergence would be -5 to 1. And it doesn't absolutely converge at -5. The place where it conditionally converges would be at -5. So the way you type that into WebWork is as a set containing just the element -5. Again, for the place where a power series conditionally converges, it's either going to be a set containing nothing, a set containing 1 point, or a set containing 2 points. So you either get no endpoints, 1 endpoint, or 2 endpoints. Those are the only options for where a power series conditionally converges. And then, okay, yeah. What was the last thing? Oh yeah, radius of convergence. We already said it, but if you look at the length of that interval, 1 minus -5 is 6, and 6 divided by 2 is 3. Yeah.
For interval convergence, it always includes an endpoint that conditionally converges.
Nope. So I'm going to say this is a general statement. Endpoints are always a grab bag. Endpoints can literally be anything. They can both absolutely converge. They could both conditionally converge. They could both diverge, or you could have one doing one thing and one doing something else. And they can literally do one of each. You can make it, I could definitely make up a series where each endpoint did one of whatever you wanted. I mean, well, up to 2 things, right? You can't get all 3 things because there's only 2 endpoints. But yeah, the endpoints are always like, you just have to check them. You have to put them into the thing.
So I just meant like, if we find out it does conditionally converge, then we do include in the buckets.
Yes, the interval of convergence we don't care if it's absolute or conditional. We want to include every point where the series would converge. And then this interval of absolute convergence is something I've never talked about before, but it would include the points where absolute convergence.
What needs to happen in order for the endpoints to absolutely converge?
Well, so like in the previous example, this one we had absolute convergence at each endpoint. So what I really did when I made up these 2 examples was when I looked at this example, I made up something. And so here's kind of what happens with these. I typically know that when I make up something like this, my endpoints are going to be something that gives me negative this number to the n and positive this number to the n. So I'm going to get like a 2 to the n and a -2 to the n. Divided by that, they're going to kind of essentially cancel each other out. And be left with either a 1 over n to whatever power I've picked there, or a -1 to the n over n to the power I picked. Well, I know that something over n to the 4th converges because P series. So I knew that when I made this one up, it was going to absolutely converge at each endpoint, because 1 over n to the 4th is an absolute convergent series, and -1 to the n over n to the 4th is an absolute convergent series. Whereas when I made this one up, I know that when I'm left with the 1 over root n, that's divergent. And the -1 to the n over root n, that's conditionally convergent. So, sorry, I kind of got off track of what your question was. What did you say again?
What's the difference? Basically, what's the difference between absolute and endpoints?
Sure. So the difference is that for this one, right? If I took the absolute value of this, it would diverge, right? This is not absolutely convergent. Take its absolute value. Oh, you get that, which we already know is divergent.
So we need to take out the value, like after one of the steps.
Right. Now, the thing is, I didn't because I already did the work for it, right? I was doing this and I was like, oh, well, I've already seen what the absolute value of that looks like right there. So I don't need to go through the steps of writing out the fact that I know it doesn't absolutely converge because I can see that from what I did right there. But I should make a mental note, oh, yeah, this is not absolutely convergent because of this. Right? There's the absolute value of that, it diverged. And that's kind of why I was saying before, you should do the one that is not the endpoint that makes it not alternate first, because that'll give you information about what the other one is going to do. Let's look at another example, unless there's more questions about this. Yeah.
So like, if an endpoint diverges, and like, then it's conditionally convergent.
No. The endpoint diverges is we're out of luck. So, right, so I would say, right, specifically, this example is not conditionally convergent at 1. Right, this series is divergent at 1. It is not being included in our set of points where it's conditionally convergent. So you can only basically those three things are all disjoint from each other. You can't be both at the same time. If you're, oh my God, words, divergent, you can't be conditionally convergent. You can't be absolutely convergent if you're divergent, right? Those two things are totally different. And if you're absolutely convergent, you can't be conditionally convergent because literally the definition of being conditionally convergent is you converge and you are not absolutely convergent. Go ahead, do it.
So like, if we have for the interval convergence thing that we're doing right now, it's like, I guess I'm confused like the interval of like, there's absolute and then there's conditional. So like,
Right. So the interval of absolute, so really the only, when for specifically for these, words I'm looking for, sorry, for these power series, the open interval will always absolutely converge. And then the endpoints are the only place where we have questions. And literally the endpoints can do anything. They could absolutely, they could conditionally, they could diverge. And they typically don't have to do the same thing. One could absolutely, one could conditional. One could absolute, one could diverge. One could conditional, one could absolute, right? It's up for grabs.
so what's the difference between conditional and absolute?
Sure.
Sorry, like,
No, these are, I'm sure you're not the only one that has these questions. So let me give you 3 examples. This series, I'm not going to write from n equals whatever because you guys know. This series diverges. We've seen it many times. It's the best. If they ask for interval of convergence, will always be a power series or no? Yeah, I mean, you only ask for the interval of convergence in this context of a power series. There's no other type of power series is just a very broad term, meaning you've got some coefficients of things times x to some power. It's a function with x's as powers. It's kind of like a polynomial, but it's not actually a polynomial because it never ends, whereas a polynomial has to stop at some highest power. But they have similar properties. So this diverges. This series converges conditionally. Meaning, so converges conditionally is words that mean 2 other things, meaning it doesn't converge absolutely. But does converge. That's what conditional convergence means. It does not converge absolutely, but it does converge. This series, 1 over n squared, the series for 1 over n squared, converges. And now we don't typically use this language because it's just baked in. But if you have a series that isn't alternating, right, this is just 1 + 1/4 + 1/9, so on, so on, so on. If it converges, it automatically converges absolutely, because it's no different than its series of absolute value terms, right? This is the same as that. So of course, if it converges, it's absolutely convergent. And that's true for any series where all the terms are all positive. If it's convergent, it's automatically absolutely convergent. But we never say that. No one would ever say, and not no one, most people would not say that this series is absolutely convergent. They would just say it converges and be like, duh, of course it's absolutely convergent because all the terms are positive. So why wouldn't it be? Like, yeah, that's, I'm trying to speak from the perspective of like some math person who's like, well, of course, right? Like, but like we should say the things. It does converge absolutely. And it's good to remind yourself, oh yeah, that is absolutely convergent. And actually, so is any convergent P series. Any convergent P series is absolutely convergent because all the terms are already positive. Any series you show that converges by the ratio test is absolutely convergent. It is a feature of the test. The same is true for the root test. So just as a matter of interest, actually, let me hold on. I'll get there in a second. On the other hand, if we were looking at this series, well, we already know it's absolutely convergent because we know what its absolute value looks like. So this is absolutely convergent, or you could say converges absolutely. It means the same thing. Because this series, which is the absolute value of its terms, that's just equal to the sum of 1/n², which is convergent. So if the series of absolute value terms converges, the original series is absolutely convergent, which means it's also convergent, right? That's why we use those words, because like we want it to mean something similar. So if something's absolutely convergent, it is convergent. So this series is absolutely convergent. We would not say, we would be incorrect to say that it's conditionally convergent. It's not conditionally convergent, because conditionally convergent means it doesn't converge absolutely. And this one does.
With the conditional convergence, it's like I can apply like the ratio test, and so it converges but it doesn't converge.
Right. So typically here's what happens when you're trying to get conditional convergence. Here's what usually happens. As a step one, you'll often show that it is not absolutely convergent. So you'll usually get that the sum of the absolute value of the terms of the series diverges. For example, the sum of -1 to the n of n. Its absolute value terms, definitely the series for that diverges. 100%. So then after you've tested for absolute convergence, then you're like, well, maybe it converges conditionally. Now you only check this if it's alternating. Because really, alternating series are the only types of series we have that are conditionally convergent. So then we're like, okay, well, then we're going to, step two, check conditional. Does the original series converge? And usually it's alternating. So we're going to check the alternating series test. So that's the process for showing something conditionally converges. It has to not absolutely converge, and then it must converge regularly. Yeah. So it depends on how. Typically, the way you will fail the AST is by showing that the limit of the sequence isn't 0, which is also the nth term test. But there are so as a what is that series? I don't remember what it is. Sine of n over n? I don't know. There are series where the alternating series test fails and you don't get that, but it's not, it's a very corner case that doesn't really come from this class. So I would say typically if the alternating series test is failing, it's usually because the limit of the terms isn't 0. And then you can be like, oh, nth term test, the series diverges because the limit of the terms isn't 0. But you wouldn't say it diverged because the alternating series test failed. You would say it diverged because the nth term test succeeded. Nope.
I saw questions on practice midterm. Prove this or is absolutely conditionally or divergent, and like trying to prove it absolutely.
Right. Right. So I would always check first for absolute convergence. Unless it's obvious to you that it diverges already. But that's like, for example, if someone gave you this series, the sum from n equals 1 to infinity of -1 to the n times, I don't know, 2n plus 3 over n plus 1. I mean, you could say, does it absolutely converge? And look at the sum from n equals 1 to infinity. Now, I don't want to write the absolute value of that thing because we know what the absolute value of that thing is going to do. It's going to make the -1 to the n plus 1 part go away. So you should just say absolute. Yeah, I'm looking at this. Does that series converge? Hell no. That series is extremely divergent. You might be answering the question in your head, does that sequence converge? And that sequence definitely converges. The sequence a sub n equal to 2n plus 3 over n plus 1 certainly converges to 2 because the limit as n goes to infinity of 2n plus 3 over n plus 1 is equal to 2. What does that mean about the series? Right, the series diverges. This diverges by the nth term test. But if that's true for the absolute value, it's also true for the alternating series, right? If this limit of this non-alternating sequence is 2, then you should just move straight to divergence. Because if you look at this series, the limit of the sequence, now this is where things might get a little slightly dicey, but just slightly. Oh, what time is it? Okay, we're close to 3. So it's not true that the limit of that sequence is 2. It's not 2. The limit of that sequence doesn't exist because it keeps bouncing back and forth between things that are closer to 2 and things that are closer to -2. But whether you're getting close to 2 or -2, what number that we need to get close to are we not getting close to? 0, right? This limit is definitely not equal to 0, but that means the series diverges because the limit as n goes to infinity of the sequence is not 0. Right? The limit not existing means it's not 0. And the limit not being 0 means the series is divergent. So when you're checking for absolute versus conditional versus divergence, check absolute first. And if it doesn't converge absolutely in a way that seems like it might converge conditionally, then look for conditional. Like if you've got like a 1 over n, like a -1 to the 1 over n. But if you've got something where it's not converging absolutely and it seems pretty clear that it might just diverge, skip the next part. But yes, to kind of answer your previous question, I would check absolute, then I would check for conditional, only if it's alternating, obviously. And then I would check for divergence. So conditional, we only check no one should be really asking you these questions if it's not alternating. These really only kind of make sense in that context. Oh, wait, you got a question? Okay, yeah, question?
So you only check if, and so it's only alternate, so only check absolute condition divergence if it's alternating, which is part of the power series. Or am I-
No, alternating is just the negative one to the n part.
Yes, you can only do that like,
And these are all, everything we've talked about today has been power series.
okay, so,
So the power series part specifically refers to the part where you have the x to a thing, right? That's what makes it the power series. Because you're trying to write a function as a sum of x's to higher and higher and higher powers. But yeah, so if your series isn't alternating, you just check for convergence. And if it doesn't converge, divergence, right? But there's no absolute versus conditional because the absolute and the original are the same. So there's no difference between the two. I feel like there was one other thing I really, oh yeah, I got 2 minutes. I got 3 minutes actually. Let me, there's one more thing I want to point out because there is one more important series we should talk about. Here's an important series. The series for e to the x, which we'll talk about how to find it next time, but I'll just tell you now, the series for e to the x is kind of really brilliant. Meaning, maybe not brilliant, but it's very lovely. It's this very nice pattern where it's just x to a power divided by that number factorial. It is worth knowing that 0 factorial is equal to 1. So x to the 0 over 0 factorial does give you 1. One way you can check this for yourself is take the derivative. The derivative of e to the x should equal e to the x. Let's see if that works out. What's the derivative of 1? 0. What's the derivative of x? How about the derivative of x squared? The derivative of x cubed. But look, what's 2 over 2 factorial? Well, that's 2 over 2 times 1, which is just 1 over 1. And what's 3 over 3 factorial? Well, that's 3 over 3 times 2 times 1, which is just 1 over 2 factorial. And 4 over 4 factorial is really 4 over 4 times 3 times 2 times 1, which is just 1 over 3 factorial. So look what we get. We get 1 plus x squared over 2 factorial plus x. Oh, look, it's the same thing we just had. All right. Interval of convergence. Ratio test. There is a point to this, and I do think you should stick around for just a minute so I can show you. It's real straightforward. So there's our ratio test, x to the n plus 1 over n plus 1 factorial times the reciprocal. And then we're going to get the limit as n goes to infinity. X to the n plus 1 over x to the n is just x. And what's n factorial over n plus 1 factorial? And then factorials cancel. Right? So right, that's just n factorial over n plus 1. Oops. That's just n factorial over n plus 1 times n factorial. And those cancel. Okay. And now, when you do this limit, you have to remember that x is a real number. So it's like 5 or a billion or whatever, but it's set. And then if you take the limit as n goes to infinity, you have a billion divided by something that's getting infinitely large. And a billion or a trillion or whatever number you want divided by something that's larger and larger and larger and larger and larger is 0. Regardless of what x is, right? Choose an x and then let n go to infinity, the limit's going to be 0. And 0 is definitely less than 1. So it doesn't matter what x is, this series converges for all values of x. So the interval of convergence is all real numbers. And yes, it is absolutely convergent on that entire interval. And the radius of convergence is?
Infinity?
Right, half of infinity, still infinity. So when your interval is everything, your radius is infinity. All right, I should stop there. It's 3:01.